As for today, we're going to continue with the logic of quantified statements. This time we're going to be dealing with statements with multiple quantifiers. When a statement contains more than one kind of quantifier, we imagine the action suggested by the quantifiers as being performed in the order in which the quantifiers occur. So the statement, for all of x in set D, there exists a y in set E such that x and y satisfy the property P of x and y. You show that such a statement is true, you must be able to meet the following challenge. Imagine that someone is allowed to choose any element whatsoever from set D, any element x, and then the challenge is for you to find an element y in E so that the person's x and your y taken together satisfy the property P of x and y. Okay. Because you do not have to specify the y until after the other person has specified the x, you are allowed to find a different value of y for each different x you are given. I really don't like the Tarski's world examples that they give, so I'm just going to kind of gloss over it. You're kind of required to flip-flop back and forth between the diagram that you're given and the following slides. So I'm going to just kind of skip over this. I don't believe there's no Tarski's world problems on exams or anything like that. So it's just a thought exercise. But let me just get past this. Okay. Interpreting statements with two different quantifiers. If you want to establish the truth of the statement of the form, all of x, or for every x in D, there exists an element of y in E such that P of x and y is true. Your challenge is to allow someone else to pick whatever element x and D they wish, and then you must find an element y in E that works for that particular x. Now for the opposite arrangement, if you want to establish the truth of a statement in the form, there exists an element in D such that for all of y in E, P of x and y. Your job is to find one particular x in D that will work no matter what y is in E is anyone might choose to challenge you with. They are different. The order does matter. An example here. College cafeteria line has 4 stations: salad, main course, desserts, beverages. They each offer different dishes, and 3 students go through the line and make the following choices. Okay. This can be represented by the diagram here. It shows who chooses what. All right, so each of the following statements informally, let's see here. There exists an item I such that all students S chooses I. Put informally, there is an item that every student has chosen. Is that true? Did everybody pick a particular item? Yes. Everybody picked pie. All right. There exists a student S such that all items I, S chose I. So there's a student that chose one of every item. That's false because nobody picked every all what 7 items? No, 9 items. There exists a student S such that for all stations Z, and there exists an item I in Z such that S chose I. So that would be there's a student that chose at least one item from every station. There exists a student that all stations an item was chosen. And yeah, and that one was true too, because Uda and Tia, I think, chose an item from both from all stations. And pardon me, for all students S and all station Z, and there exists an item I in Z such that S chose I. Every student, and every station, there was an item chosen by S. So for did all students pick one item, at least one item, from every station? In this case, it's false because Yuan did not choose a salad. So the solutions are here. And translating from informal to formal language. All right, let's see here. Most problems are stated in informal language, but solving them often requires translating them into more formal terms. Formal terms are more concrete and can be more easily manipulated. So translating them into formal language is an important skill. Let's see here. Translating statements with multiple quantifiers from informal to formal language. The reciprocal of a real number A is a real number B such that A times B equals 1. The following statements are true. Which of them formally using each of them formally using quantifiers and variables? Every non-zero real number has a reciprocal. For all x that are real numbers, there exists a number such that the real number y, that y times x equals 1, or A and B. Let's see here. And there is a real number with no reciprocal. There exists a real number A and let's see here. The real number C such that all real numbers D, C times D is not equal to 1. So non-zero real number U, there exists a real number V such that U times V equals 1. which is true, and there's also there exists a real number c such that for all real numbers d, c times d does not equal 1. That real number c would be equal to, of course, 0. Okay. This one I had to look over a few times to get this one straight in my head. The definition of a limit of the limit of a sequence studied in calculus uses both quantifiers a for all and there exists, and also if then. We say that the limit of a sequence a sub n as n goes to infinity equals L, and write this here. If and only if the values of a sub n become arbitrarily close to L as n gets larger and larger without bound. Okay, so this means that any given positive integer epsilon, we can find an integer n such that whenever n is larger than capital N, the number a sub n sits between L minus epsilon and L plus epsilon on the number line. So in formal symbolic terms, you get this. And the authors admit the logical complexity of this definition. It's no wonder that many students find it hard to understand. But as n gets larger, epsilon actually gets smaller, if I'm not mistaken. Ambiguous language. Why this slide was put in here, I have no idea. It doesn't relate to anything. I'm sure you've seen this picture before. It can be taken two ways, and either the profile of a young woman or the face of an older woman. Why that was thrown in here, I really have no idea. But there you go. Negations of statements with more than one quantifier. You can use the same rules to negate statements with several quantifiers that you use to negate simpler quantified statements. For example, the negation of all x and d p of x is there exists an x in d such that not p of x. And the negation of the existing of there exists an x in d such that p of x means that for all of x in d, not p of x. So you link these together and get for a universal quantifier followed by an existential quantifier. You get the existential quantifier with the negation of the existential quantifier. So it switches them around. There exists, it's an existential quantifier followed by a universal quantifier and the negation of the property. So you're kind of flipping everything around. You flip the order of the quantifiers and invert the property that they would satisfy. Similarly, if the existential comes first, you have the universal followed by the inverse of the universal, which turns into an existential with the inverse of the property. So negations of statements with two different quantifiers are summarized here. All right. Again, with the Tarski world thing, and gloss over this, or pass on from this, because it's just a way of giving an example, but would require flipping back and forth, and I don't want to spend the time doing all that. The order of quantifiers. Consider the following two statements. For all persons X, for every person X, there exists a person Y such that X loves Y, which informally means that for every person, there's another person that the first person loves. Okay? Whereas if you flip the order of the X and Y to be there and exists a person Y such that all persons X loves Y, means that there's one amazing individual who is loved by all people. Well, obviously these mean two very different things. So the order of the quantifiers does matter. It affects the meaning greatly. Now, the exception to this is if one quantifier immediately follows another quantifier of the same type, then the order of the quantifiers does not affect the meaning. So if it's two universal quantifiers or two existential quantifiers, the order doesn't really matter. Whichever one makes more sense to you. Consider the commutative property of addition of real numbers. For all real numbers X and all real numbers Y, X plus Y equals Y plus X. This means the same as for all real numbers Y and all real numbers X, X plus Y equals Y plus X. Thus, the property can be expressed a little less formally as for all real numbers X and Y, X plus Y equals Y plus X. Again, with the Tarski world thing. Doesn't really make sense unless you have two boards, one with the diagram on it and one with the questions on it. Otherwise, it's just cumbersome. Formal logical notation. In some areas of computer science, logical statements are expressed in purely symbolic notation. This is pretty much true. The notation involves predicates to describe all properties of variables and omitting words such that in existential statements. The formalism also depends on the following facts. For all X and D, P of X can be written for all X, X in D. If X is in D, then P of X. And there exists in D such that P of X can be written as X if X is in D and P of X. So, and again with the Tarski world nonsense. All right, let's see here. Okay. The disadvantage of fully formal notation is that because it is complex and somewhat remote from intuitive understanding, when we use it, we make errors that go unrecognized. Let's see here. These operations can be made completely mechanical and programmed on a computer, however. Taken together, the symbols for quantifiers, variables, and predicates and logical connectives make up what is known as the language of first-order logic. Anybody here ever heard of Prolog as a computer language? No? It's been around a while. I programmed in it when I was younger. It's an odd language, but the Prolog, the name comes from programming and logic, is what it is. It's just logic statements. A simple Prolog program consists of a set of statements describing some situation together with questions about the situation. In the language, there are search and inference techniques needed to answer the questions by deriving answers from the given statements. Frees the programmer from the necessity of having to write separate programs to answer each type of question. So it's a pretty high level language. You don't write a whole lot to get you don't write a whole lot of code to get the results that you want. Consider the following picture. Gray is above B1, blue 1 and white 1. White 2 is above B2 and blue 2 and blue 3. All right. This can be expressed in Prolog as these lines of code. Is above means gray is above B1. Is above B1 over B is over W1, and so on and so forth. And what color is each block? And so you ask the question, is the color, or is B1 blue? And of course, from this, it finds that relationship and answers yes. Is anything above W1? Well, that's a little bit more complex. It would return 2, because if you recall, W1 is at the bottom of this. It would return B1 and gray and G. So, this goes through the logic of those statements. And is this where Prolog makes people kind of scratch their head is it gives it can give multiple answers to one question. It doesn't just get just one answer, the first answer, and return that and be done. It can return multiple. However, it must infer the solution x equals g from the following statements. G is above B1, B1 is above W1, is above XZ, is above XY, and is above YZ. Now, so these would have to go back to the diagram for those, but let's see here. Is B2 above W1? No. What colors X is the predicate W is colored X true? So the answer is X is white. The question means for what blocks is the predicate X is colored blue true? And the answer is X is B equals B1, X equals B2, and X equals B3. So it can return multiple statements. And I believe that is it for that section. So I'll go back to the home. Chapter 3. And finish off logic of quantified statements with a board that doesn't want to cooperate today. All right. Arguments with quantified statements. So the rule of universal instantiation says the following. If a property is true of everything in a set, then it is true for any particular thing in that set. Basically, if it, like I said, if it's true for the whole set, then any element in the set, the property is also true. So, or more, a particular case follows as a special instance of its more general or universal truth. The validity of this argument form follows immediately from the definition of the truth values for a universal statement. One of the most famous examples of universal instantiation is the following. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. So, using the same type of argument, suppose we have the problem that requires you to simplify x to the k plus 1 times r, where r is a particular real number and k is a particular integer. You know from your study of algebra that the following universal statements are true. For every real number x and all integers m and n, x to the m times n x to the n equals x to the m plus n. And for every real number x, x to the first power is equal to x. So you proceed with substituting r for r to the power of 1. And r is, then it goes to r is to the k plus 1 plus 1. Simplify that to r to the k plus 2. So, the reasoning behind the steps. For every real number x, x to the power of 1 is x. R is a particular real number, therefore r to the power of 1 is equal to r. And then for every real number x, for all integers m and n, x to the m times x to the n equals m plus n. R is a real number, k is plus 1, and 1 are k plus 1 and 1 are particular integers, therefore you get that result. These are both examples of universal instantiation. Now, universal modus ponens takes the modus ponens that we learned in, what was that, chapter 2? and applies it to that. So for all x, if p of x, then the q of x, p of a then is true for a particular a, then q of a is true by modus ponens. Following argument using quantifiers, variables, and predicate symbols. Is this argument valid, and why? If an integer is even, then its square is even. K is a particular integer that is even. Therefore, k squared is even. So the major premise of this argument can be rewritten as, for all x, if x is an even integer, then x squared is even. Let e of x be x is an even integer. Let s of x be is even. And let k stand for a particular integer that is even. Then the following argument, the argument has the following form. If e of x, then s of x for all x. E of k is true for a particular k, therefore s of k is true. It is valid by universal modus ponens. Write the conclusion that can be inferred using the universal modus ponens. Triangle shown on the right is a right triangle with both legs equal to 1 and a hypotenuse C. All right. Right triangle, yeah. So if T is any right triangle with a hypotenuse C and legs A and B, then C squared plus A equals A squared plus B squared. So if you take the non-negative square root of both sides of the equation, you obtain C equals the square root of 2. This shows that there is a line segment whose length is square root of 2. Use of universal modus ponens in a proof. The thing got screwed up a little bit. Boy. Here's a proof that the sum of any two even integers is even. It makes use of the definition of an even integer, which is even if and only if it equals twice some other integer. Or more formally, for all integers x, x is even if and only if there exists an integer, say k, such that x equals 2k. Suppose m and n are arbitrarily chosen even integers, then m equals 2r for some integer and n equals 2s for some integer, s. Therefore, m plus n equals 2r plus 2s by substitution. Factor out the 2 and you get 2 times the quantity of r plus s. Now, r plus s is an integer because the sum of two integers is an integer. And so 2 times the quantity r plus s is even. Thus, m plus n is even. Let's see here. This is the expansion of the proof. Universal modus ponens is used in the first section of the proof. Modus ponens again in the second step of the proof. And third is another universal modus ponens. Then it uses the distributive property to factor out the 2 from the 2r plus 2s. And then modus ponens again to indicate that r plus s is a integer. And then universal modus ponens again to show that 2 times the quantity r plus s is even. Now, universal modus tollens, similar in nature, but it results from combining universal instantiation with modus tollens. Modus tollens is the heart of proof of is at the heart of the proof of contradiction, which is a important method of mathematical argument. So for all of x, if p of x, then q of x. If that's true, and if not q of a is true for a particular a, then not p of a. Rewrite the following argument using quantifiers, variables, and predicate symbols. Write the major premise in conditional form. All human beings are mortal. Zeus is not mortal, therefore Zeus is not human. If a major premise can be written as, if for all of x, if x is human, then x is mortal. Let h be x is human, and let m be x is mortal. Let z stand for Zeus. This argument becomes this here. This argument has the form of universal modus tollens and is therefore valid. What's the conclusion that can be inferred using universal modus tollens here? All professors are absent-minded. Tom Hutchins is not absent-minded. Therefore, Hutchins is not a professor. Proving the validity of arguments with quantified statements. All right, definition. Valid means the following. No matter what particular predicates are substitute for the predicate symbols and in its premises, if the resulting premise statements are all true, then the conclusion is also true. An argument is valid if and only if its form is valid. It is called sound if and only if its form is valid and its premises are true. So, using diagrams to test for validity, kind of using Venn diagrams. Consider the statement, all integers are rational numbers. Picture the set of all integers and the set of all rational numbers as disks, or circles, or whatever. And the truth of the given statement is represented by placing integer disk entirely inside the rational's disk. All right. Because the two statements, for all x elements of D, Q of x, and for all x, if x is in D, then Q of x are logically equivalent. Both can be represented by diagrams like the foregoing, like what was on the previous slide. Use diagrams to show the validity of the following syllogism. All human beings are mortal. Zeus is not mortal. Therefore, Zeus is not a human being. So you would have the mortals and human beings circles, and the second premise, the minor premise, the mortals with Zeus being outside the mortal's disk. Since all human beings are in the mortal's disk, Zeus cannot be in the human being's circle. So basically the dot is outside the mortal's disk. It is necessarily outside the human being's disk. Thus the conclusion follows necessarily from the truth of the premises. It is impossible for the premise of this argument to be true and the conclusion false, hence the argument is valid. Now, use a diagram to show the invalidity of the following argument. All human beings are mortal. Felix is mortal. Therefore, Felix is a human being. Not necessarily true, because Felix is somewhere in the mortal's disk, but not necessarily within the inner disk of the human beings. So it's not necessarily true. As they say here, Felix might, for example, be a cat. Cats are also mortal, but not human beings. Because the conclusion does not necessarily follow from the premises, the argument is invalid. So, converse error. If P then for all of x, if P of x, then Q of x, Q of A for a particular A, therefore P of A. That's an invalid conclusion. This is converse error. We saw this before in the conditionals section. The argument form is invalid, and it exhibits inverse error. Inverse error is similar, where if P then Q, not P for a particular A, therefore not Q. Also a invalid conclusion. Use diagrams to test the following argument for validity. No polynomial functions have horizontal asymptotes. This function has a horizontal asymptote, therefore this function is not a polynomial function. Good way to represent this is diagrammatically. Minor premise is placing the dot labeled this function inside the disk for functions with horizontal asymptotes. And a circle for the polynomial functions. This shows that this function must lie outside the polynomial functions disk, and so the truth of the conclusion follows from the truth of the premises. Hence, the argument is valid. Creating additional forms of argument. Universal modus ponens and modus tollens are obtained by combining universal instantiation with modus tollens and modus ponens. In the same way, additional forms of arguments involving universally quantified statements can be obtained by combining universal instantiation with other valid argument forms, such as transitivity. If P of X, then Q of X, and if Q of X, then R of X, therefore, if P of X, then R of X for all of X. And again, for Tarski's world, skip that. Yeah. This example is convoluted and bizarre. But remark on the converse and inverse errors. Getting close to the end. One reason why so many people make converse and inverse errors is the form of the resulting arguments would be valid for if the major premise were a biconditional rather than a simple conditional. For example, all the town criminals frequent the den of iniquity. John frequents the den of iniquity. Therefore, John is one of the town's criminals. Not necessarily true. It is invalid. It results from converse error. Therefore, it may be false even if when the premise of the arguments are premises of the argument are true. This is guilt by association type of thing going on here. The closer the major premise comes to a biconditional, the more likely the conclusion is to be true. If hardly anyone but criminals frequent the bar, then John also frequents the bar, then it is likely, though not certain, that John is a criminal. Still not enough to convict him. A variation of converse error is useful for a reasoning tool, provided it's used with caution. It is the type of reasoning that is used by doctors to make medical diagnoses. For example, for every x, if P of x, then Q of x, Q of A is true for a particular A, then check out the statement P of A it just might be true. So in the example of a patient that has the symptoms of pneumonia, if X has pneumonia, then he has fever, cough, feels miserable. And suppose the doctor knows that John fits the bill on this, he would then attempt to gain further support for the diagnosis through laboratory testing that is specifically designed to detect pneumonia. The closer a set of symptoms comes to being a necessary and sufficient condition for an illness, the more nearly certain the doctor can be of his or her diagnosis. So you can use the converse error to diagnose problems, and with cars, with people, with computer code, that sort of thing. You just got to remember that you have to test for the validity of the major premise. Anyway, that just about wraps it up for today. Quiz on Chapter 3 on Tuesday. I wrote it up today, so fewer questions than the last quiz, so not as It shouldn't take as long as the last quiz, hopefully. But be ready for that on Tuesday. Notes, of course, are welcome and allowed to be used. Have a good afternoon.